Good morning, all. In the previous classes, we have studied about slot antenna and its application. Now, in this class, we will discuss about horn antenna and its application. At the end of session, the students will be able to know the construction of horn antenna, know the different basic types of horn antenna, know the different advantages, disadvantages, and applications of horn antenna. Now, we will see what is an horn antenna. So, horn antenna is a type of aperture antenna which is specially designed for microwave frequencies. The end of the horn antenna is widened or in the horn shape. Because of the structure, there is a larger directivity so that the emitted signal can be easily transmitted to long distances. Horn antenna operates in microwave frequency, so the frequency range of this antenna is super high or ultra high range, which ranges from 300 MHz to the 30 MHz. These antennas are used as feed horns for big antennas like parabolic reflector antennas, directive antennas, etc. The benefits of using these antennas are simplest design and simple to adjust, low standing wave ratio, moderate directivity, and broad bandwidth. In generally, if we take a waveguide, if we cut the waveguide at one end and we excite, give it the input on the other end, the waveguide will also radiate into the free space. But because of sudden discontinuity of that waveguide on one side, the reflections will occur. It will not properly match with the free space impedance. So that's why more reflections will occur. To avoid this problem, the other end of the waveguide is flare diode. That flare diode structure is called as horn. So because of horn structure, the sudden discontinuity is converted to the gradual discontinuity. So because of this sudden discontinuity to the gradual discontinuity, the impedance mismatch problem will be rectified. The impedance will be properly matched. The waveguide impedance is properly matched with the free space waveguide. So the reflection waves will be reduced. Antenna design and working. Horn antenna design can be done with the flared waveguide, which is formed as an horn. These are used to transmit and receive RF microwave signals. Usually, these are used in combination with the waveguide feeds and direct radio waves within a narrow beam. Here, the flared portion can be in any shape like square, conical, and rectangular. For proper working, this antenna should be in minimum size. If the wavelength is very large or the horn size is very small, then the antenna will not work properly. In this antenna, the fraction of incident energy can be radiated from the entry of the waveguide, and the rest of the energy will be reflected back from the same entry because of open entry. The poor impedance matching will exist in between the space and waveguide. Also, the edges of the waveguide. Diffraction affects the poor radiating capacity of the waveguide. So, to overcome the drawbacks of the waveguide, its end is opened in an aldermanic horn form so that a smooth transition can be allowed in between the space and waveguide, thus offering better directivity towards the radio wave. So this is the horn antenna diagram. So this is the waveguide, rectangular waveguide. The rectangular waveguide one end is flare diode. Okay, this flare diode will send and receive, transmit and receive the signals. Because of this flaring out of this waveguide mouth, the sudden transition is converted into the continuous transition so that it will properly matched with the free space impedance. By changing the waveguide like a horn structure, the discontinuity in between the space and waveguide 377 ohms impedance is eliminated. So this provides the incident energy to be emitted in the forward direction by decreasing the diffraction on the edges. Therefore, the transmitting antenna's directivity can be enhanced with superior gain. The working of the horn antenna is as follows. Once the waveguide one end is excited, then the field can be generated. In general, the fields within the waveguide and free space will transmit in a similar way. But in the case of propagation with the waveguide, the propagation field can be controlled through the waveguide walls, so the field will not pass spherically, as this is not the case through the free space propagation. Once the traveling field arrives at the waveguide end, then it transmits in the same way as the free space. So at the waveguide end, the spherical waveforms can be obtained. So in the horn antenna, the plane wavefront can be converted into the spherical wavefront. That is important point to notice. So types of horn antenna. Horn antennas are classified into different types: pyramidal, conical, and exponential. First, we will see the pyramidal horn antenna. As the name suggests that the antenna is a pyramid shape. The horn of the antenna is in a pyramid shape. Through a rectangular cross section, this antenna can be formed by flaring both the waveguide walls. So we have two type of waveguide walls, where vertical waveguide wall and horizontal waveguide wall. Both ends are flared out simultaneously, and the pyramidal horn antenna is formed. In this antenna, rectangular waveguide is utilized. The flaring can be done with both the direction of magnetic and electric field vector E and H. These antennas are simply used to radiate linearly polarized radio waves and used with the rectangular waveguide. Sectorial horn antenna. Previously, we have seen pyramidal horn antenna, in which both the walls of the waveguide are flared out. But here, in the sectorial horn antenna, only one side of the wall is flared out. Instead of two sides, horizontal and vertical, either horizontal or vertical is flared out. It is a type of antenna where only one pair of faces are flared, whereas the other pair is in parallel. It generates a fan-shaped thin beam in the flared side plane, however, broad in the narrow side plane. These type of antennas are frequently used as feed horns, especially for wide search radar antennas. So in this antenna, flaring can be performed simply through one of the waveguide walls. Further, these are classified into two types: E-plane and H-plane. E-plane. What is E-plane sectoral horn antenna? Once one of the waveguide walls in the antenna is flared with the electric field vector, direction is called E-plane antenna. Once the waveguide walls in the antennas are flared with the magnetic field vector direction, then it is called as H-plane antenna. H-plane antenna. So this is the sectorial horn antenna. Previously we have seen pyramidal horn antenna, sectoral horn. Only one side is flared out. Remaining side is kept constant. So this is conical horn antenna. Conical horn antenna is formed by the flaring out of circular waveguide. This is rectangular waveguide. This is circular waveguide. Flaring out of circular waveguide will produce the conical horn antenna. So this is the aperture of the conical horn. Conical horn antenna. When an antenna horn is in the cone shape with a circular cross section is known as conical horn antenna. These antennas are simply used to cylindrical waveguide or circular waveguides. A conical antenna formation is an effect of circular waveguide flaring. A circular horn antenna can be either biconical or conical within the nature. So we have discussed. So this is the sectoral H plane. That means H direction, the walls are flared out. In the E direction, the walls are flared out. Okay. Here, pyramidal horn is produced by flaring out both E plane and H plane. Okay. This is the conical horn. The conical horn is obtained by flaring out of circular waveguide or cylindrical waveguide. These are the four type of horn antennas: sectoral H-plane horn antenna, sectoral E-plane horn antenna, pyramidal horn antenna, and conical horn antenna. Hope you understand. Next, design equations of horn antenna. So this is the horn antenna parameters. So this is the waveguide. This is the flared out part of waveguide. So this is known as delta. Okay, nothing but path difference. Okay, this is L. Okay, yeah, sorry, this is L, axial length. This is the D, nothing but the aperture dimension, and this theta is nothing but the flare angle. Okay, So this is the diagram of the horn antenna. Okay. So in this, the delta is the path difference, L is the axial length, and D is the aperture or open mode, and theta is the flare angle. These are the design equations for horn antenna. The L is nothing but the axial length of the is given by D square by 8 delta. D square means the aperture dimension. The length is given by D square by 8 delta. The theta is nothing but the flare angle. It is given by tan inverse D by 2L. Okay, or 2 cos inverse L by L plus delta. This is obtained from the triangular equations. Okay, so these are the design parameters of horn antenna. So off power beam width of the horn antenna is given by theta E is equal to 56 lambda by DE. Theta H is given by 67 lambda DH degrees. The directivity of horn antenna is given by D is equal to 7.5 A by lambda square. The power gain is given by GP is equal to 4.5 A by lambda square. A is nothing but DE into DH, physical area of the aperture. For conical antenna, the AE is equal to pi d. Nothing but it will be circular, so it is a pi d. So where d is the aperture diameter. So these are for rectangular horn. This is for conical horn. So where theta E is nothing but the HPBW in E plane, theta H is nothing but HPBW H plane. DE is nothing but aperture in E plane in free space. DH is the aperture for H plane in the free space wavelength. These are the important design equations for the designing of horn antennas. Next, we will see the radiation pattern of horn antenna. Okay, so the horn antenna radiation pattern is a spherical waveform. That means it converts the plane waveform into the spherical waveform. The waves move a spherical waveforms to downward of the horn through their source at the top of the horn known as the phase center. The electric and magnetic field pattern at the aperture plane at the entrance of the horn will determine the radiation pattern. As the waveforms are spherical, then phase will be increased smoothly from the aperture plane edges to the center. Due to the dissimilarity within the center point length of the edge points from the apex point, which is known as the phase error. The error will be increased through the flare angle. So increase the beam width and decrease the gain by providing with wider beam width horns than parabol dishes. Once the horn size is increased, then the phase error will be increased and provide a wider radiation pattern to the horn. Maintaining the beam width narrow needs a longer horn to maintain the phase error stable. The rising phase error restricts the size of the aperture for practical horns to 15 wavelengths because the larger aperture need long horns especially, so this restricts the practical horns gain to 30 dBi, the equivalent smallest beam width to 5 to 10 degrees. So this is the radiation pattern of the horn antenna. It will convert the plane waveform into the spherical waveform. Advantages of the horn antenna. So these are the advantages of horn antenna. These antennas can operate over a wide bandwidth, wide range of frequencies since they do not have resonant elements. The beam width of the horn antenna is 10:1 ratio, 1 GHz to 10 GHz, which is common, and 20:1 is also possible. The designing of horn antenna is very simple. They are also simple to construct to the waveguide and coaxial feeder. The antennas have very low standing wave ratio, good impedance matching. Its performance is stable for an entire range of frequencies. Small minor lobes can be formed. These antennas are used as feed horns for large parabolic antennas. Better directivity, avoid standing waves. Non-existence of resonant elements within the construction allows it to work over a wide bandwidth. It is extremely directional within nature, thus providing high directivity. It provides very less reflections. These are the disadvantages. The disadvantages of horn antenna include the following. The antenna will radiate energy in spherical waveform shape. That antenna does not provide a direct to or sharp beam. They have limited gain like 20 dB. So in order to enhance the antenna gain, the opening of the horn should be made larger so that the length of the horn will become excessive. Flare angle design will decide the directivity. The length of the flare and flare angle should not be extremely small. The antenna's directivity depend upon the flare angle. The flare dimension must be adequately large, otherwise it will make the antenna bulky sometimes. Applications. The application horn antennas are given below. These are used mainly for astronomical studies, micro-based applications to feed antenna elements like parabolic reflector antenna. These are used in laboratories to measure different antenna parameters. At micro frequencies, these are used wherever moderate gains are adequate. The horn dimensions must be high or for high gain to use the moderate gain operations. These type of antennas are applicable in speed and enforcement cameras to keep away from the reflections that interrupt the desired response. Parabol reflectors can be excited by feeding elements like horn antennas, so the higher directivity through this antenna permits it to light up the reflector. These antennas are very popular in the micro region, which provides less VSWR, high gain, fairly wide bandwidth, etc. Thank you. In the next class, we will discuss about the some more antennas.